Hey, pre-calc students, this is Mr. Beck. Today we're going to begin our talk about trigonometry. Trigonometry is really what I consider the Triforce in action, where trigonometry is going to take a lot of the geometrical ideas that we did a couple years ago. We're going to combine them with a lot of algebraic skills and put them together, and boom, we have trigonometry. So to start off with trigonometry, what we want to do is we want to talk about angles. So we could draw angles in a lot of different ways. We can draw angles like so. So there's an angle there. If you remember from geometry, you usually put like a little arc there. So we can have the angle looking like this. We want to say, okay, how are we going to standardly write every single angle? Just because we want to start off with a formal basis of how we're going to be doing everything. So we have what's considered a standard position. So the standard position of an angle is the vertex is at the origin of the rectangular coordinate plane. So let's take a look at the angle that I have right here. So we have the vertex of that angle at the origin of the coordinate plane. And then we have the initial side. So the initial side is kind of the beginning. If you remember, like within the angle, we have one side that goes to the other. We even name it that way. So if we have an angle like BAC, it's angle BAC, then we always start off with, okay, first point to the second point to the third point. So our initial side is always going to be on the positive x-axis. So initial side is positive x-axis. And then the terminal side is wherever the angle ends up. That terminal side opens up to a certain angle degree. And you guys are very, very familiar with degrees. And we're going to start with degrees, and then we're going to convert to something new. That something new is called radians. Um, so coterminal angles, you should see that all three of these angles right here do look the same, but they are not created the same. So that's why they're called coterminals. Coterminal angles are terminal side is in the same location. Just because it's the same location doesn't mean it's the exact same thing though. Now, I estimated this angle right here to be about 35 degrees. So if you see how this angle is created, we start from the initial side, we open up to the terminal side. But for the second one, we actually are going backwards to create that angle. So when we go backwards to create that angle, it no longer has the same degree measure. In fact, there are 360 degrees in a circle. What we could do is we could say, okay, we've gone backwards 360 minus that 35 that was right here to be 325, but that negative as an angle represents the direction. So the direction, positive direction is going to be going in this manner, basically quadrant 1 of the coordinate plane. And then the negative direction, we start off at quadrant 4 of the coordinate plane to go backwards. Now this third one, we take that initial 35 degrees and then we add another full circle to create it. And so 360 plus 35 is 395 degrees. So what that means is 35 degrees, negative 325 degrees, and 395 degrees are all what we call coterminal. Then we have something called quadrantal angles, and they're very important. Quadrantal angles are the angles in the standard position whose terminal side will lie on the x or the y axis. So what's simple here is 0 degrees right here is a quadrantal angle. 90 degrees right here is a quadrantal angle. 180 degrees is a quadrantal angle. And 270 degrees is a quadrantal angle. Basically, we can keep going if we wanted to. 360, 450, 540, 630, 720, etc., etc. We can always go backwards, but any multiple of 90 degrees is called a quadrantal angle. Now, kind of something that I like to point out, you know how we have the quadrants listed as 1, 2, 3, 4. I don't know if you guys have ever really wondered why did the coordinate plane, or why do we write our quadrants in that manner? Well, it actually has to do with the trigonometry that we're doing, that we start in our standard direction. We go counterclockwise from quadrant 1 to quadrant 2 to quadrant 3 to quadrant 4. But anyway, so any angle that's in quadrant 1 is from 0 to 90 degrees. Any angle that's in quadrant 2 is from 90 to 180. Quadrant 3 is 180 to 270. And quadrant 4 is 270 to 360. We can always go backwards. If we went backwards this way, then that would be from negative 90 degrees to 0, then negative 180 to negative 90, negative 270 to negative 180, negative 360 to negative 270. And we can keep going around and around as many times as we want. But anyway, first thing that we need to do, our first set of skills are, can we draw the following angles and state the quadrant that it lies in? So the first one is a 150-degree angle. The way that I think about a 150-degree angle, I kind of look at a straight line as 180, which is like so. And then if we know 90 is like about there, 180 is 60 degrees beyond 90. So how do we actually draw out that as a solution? Our initial side, our initial side is on the positive x-axis, and then the terminal side is 90 degrees plus an additional 60 more. And yes, we know that's in quadrant 2 because that's from 90 to 180. Negative 45, we start off with our initial side on the positive x-axis, and then we go, so if this is 90 degrees, and half of that's 45, and you should start understanding these relationships a little bit more because we're going to be working with them over and over again. One thing that I want to caution you on, and all the things I'm talking about when it comes to these angles and some known angles, you guys are going to really want to know how to come up with these angles, because you want to know how to do all these angles and very, very efficiently, because it's going to come back to haunt us. All right, with our third angle is at 1500 degrees. Now, something like this, it's a lot easier for us to be able to draw this if we break it down into 360 degrees. How many times does 360 degrees go into that 1500? So if you see, I wrote it as 4 times 360 plus 60, which is true. I know most people don't like to think that way, but it's very, very helpful where we have one 360 degrees, and then another one, which gives us to, oops, that tool did not like what I was just doing there. Okay, so one 360 degrees, then another 360 to be 720, and then another 360 degrees to be, I can math, 1060, and then another 360 degrees to be 14. It's 1440. I'm not sure if I said that other one right. I apparently can't math. And then, so that's 1440, and then plus another 60, which would be ending up in quadrant 1. And I think I failed to mention that was quadrant 4 in the last one. And then for D, negative 510 degrees, we start off by going negative 360, and then we have to go an additional 150 degrees. So understanding about where on the, or where inside of our 0 to 90 range we're talking about. You know, these are all estimates, and I mean, I know these are all estimates, but understanding that's going to be very, very essential throughout the course of the semester. And these numbers I'm working with are all like multiples of 30, 45, and 60. There's a reason for that, something that we did in trigonometry. So hopefully with this, you know how to draw your angles. Now, as annoying and as obnoxious it is to draw all of those like directions, all the circles that I did here specifically with C and D. Well, that is annoying. It's something that you have to do, and the reason why is because if you go back to what I started with, all 3 of these are going to look the same, and we have to show how these angles are created based off of the direction and like how many times we do go around to get to that terminal side. All right, second set of skills that we want to learn today is about converting between degrees, minutes, and seconds. The big question that I tend to ask, or I tend to ask my students is, okay, well, how many degrees are in a circle, which is 360 degrees? So if we divide that circle into 360 parts, we get 1 angle. And then we say, okay, is there anything smaller than a degree? Well, what we could do is we could break that degree into what we call minutes, and minutes are going to have this notation, that apostrophe. And then just like minutes are broken into seconds, we could take that degree, break it into 60 minutes, and each minute we could break into 60 seconds. Now we can actually do this, we could break seconds down into something smaller. They don't have a name. They're just considered like parts of a second. But the reason why this is important actually has to do with geolocation on the Earth. because the Earth, we do have 360 degrees going around the Earth. When we talk about like lines of latitude and lines of longitude, with those 360 degrees, 1 degree on the Earth is actually a pretty big distance. I think I checked one time. So from our school in Carmel, Indiana, down to I want to say down to past Indianapolis, it's in southern Indiana, would be about 1 degree. So 1 degree on the Earth is actually a pretty big distance. Um, Now, when you talk about, oh, let's break it down into 60 different parts, 1 minute would be from about where we were at in Carmel High School. 1 minute goes down to, I want to say it's on the north side of Indianapolis somewhere. It's been a couple years since I did this. Now, the more important thing is 1 minute. 1 minute is from where we're at in Carmel High School all the way up to 146th Street. Um, so actually, it's not even that far. So it's a little bit closer. But 1 minute is something, or 1 second is something you can see or see pretty clearly. I think 1 minute is 146th Street. And then 1 second is something very visible where we could walk that distance. So, anyway, our goal is to convert between degrees, minutes, seconds, and decimals. So degrees, minutes, seconds, and then decimals as a degree. So I have something that looks like 50 degrees, 48 minutes, and 18 seconds. And my goal is to convert that to a decimal in degrees. So we know it's at least 50 degrees, and you can see the answer here. It's 50.805. So we know it's a little bit more than 50 degrees because we start off at that 50, and then we're going to go almost another full degree, and then even just a little bit further. Well, it goes back to how many minutes are in a degree. There are 60 minutes in the degree. So what we do is we take that fractional portion and say, okay, we have 48 minutes out of the 60 minutes, which would take us to another part of the degree. And then we have 18 minutes or 18 seconds, and we know that there are 3,600 seconds in a minute. So, sorry, 3,600 seconds in an hour. So what that means is we say, okay, 48 out of 60, because we have that fractional portion of a degree, and then 18 out of the 3,600 of another degree, and then we can add those together. Now with these numbers, I did them so they're easy to do without a calculator. And my challenge for you is to do as many of these without a calculator as possible. That's going to be the important thing, because the more you rely on the calculator, the less that you're getting your mind to connect those numbers together. More importantly, the fractional relationships together. I know you've heard math teachers say this over and over and over again, that the calculators have hurt your thinking, but what's going to be important for trigonometry is all about fractions. Because it's all about fractions, they need to work with that fractional relationship. It's kind of like doing fundamental exercises with your mind. Just try to work with the numbers that we have as much as possible. If you need a calculator at some point, you need a calculator. It's a wonderful tool. But if you rely on the calculator to do all the basic calculations, you're going to find yourself struggling when everybody else is going to be succeeding. So anyway, so we're going to take our 48 minutes divided by 60. 48 divided by 60 is 4/5, which I can write as 8/10 because that's 0.8. And then 18 out of 3,600. Ooh, not mean to do that. 18 out of 3,600. That's like 1 over 200, which is a half over 100. And why do I say half over 100? Because it's a half of 100. Now, do you think that way? Possibly not, but it doesn't make sense. That's the important thing, because the more you're exposed to how to think through some numbers, the better off you are. So 50.805. So basically, we take all of our minutes divided by 60, take all of our seconds divided by 3,600, and add those decimals together. So the second portion I have of this is what happens if it's a negative. And if you notice, this is the exact same problem. The difference is it's negative. Now, this always catches people, because what happens is this means that we are going in the negative direction. So we go negative 50 degrees, but then the minutes and the seconds, we have to go an additional distance. So that additional distance, remember, the negative represents direction. So if we have decimals that, or if we have degrees that are negative and we're converting to degrees, yes, we do add these up, but keep in mind the perspective of this is a direction. So we're going a little bit further than 50 degrees. So yes, we add all of those up, and then we take the negative of all of that. The biggest mistake I see people make is saying, oh, -50 plus 0.8 plus 0.005, which gives you a number less than 50. So this is absolutely bad. Please do not do that. Do not do that. Remember, it represents direction. We do all of that first, so that negative is representing the negative of the whole thing. All right, problem number 3. Now we're going to go backwards. So to go back to degrees, minutes, seconds, what we're going to do is we're going to take only the decimal portion and then multiply by 60. So if I have this 123.06 degrees, I know I have 123 full degrees. Now, how many minutes and how many seconds? Well, I take that 0.06 and I multiply by 60 to figure out how many full minutes I have. And it turns out in this case, I have 3 full minutes. So when I have 3 full minutes, I'm going to go ahead and record that, 3 full minutes. And then I still have a decimal portion. That decimal portion, I have to multiply by 60 again, so I can find the number of seconds. So 0.6 times 60 is 36, give me 36 seconds. So 123 degrees, 3 minutes, 36 seconds. Basically, we multiply by 60, or take the decimal portion, multiply by 60, then take that decimal portion, multiply by 60 again. And then we get into something called the radian. Now, hopefully everybody's okay with this. We did a lot of work extensively with degrees. You guys are very, very comfortable with degrees, but now we're going to switch. And so a lot of students start grumbling and groaning at this point, going, oh, I was just happy with degrees. I've worked with degrees all my life. We have something called a radian, and a radian is another way that we can do some measuring. I want you to focus on the side of the screen here. Hopefully, there you go. So what is a radian? So a radian is based off of what we call a radius. So we know a radius creates a circle. So that radius creates a circle. We're going to take that length of the radius and we're going to apply it on the outer edge of the circle. And that's what we call 1 radian. So 1 radian, if you notice, this looks like it's a little bit around 60 degrees, but 1 radian around the circle, 2 radians, 3 radians, well, halfway around the circle is pi radians. So, and then all the way around the circle is 2 pi radians. What this means is the circumference of a circle is 2 pi r, and that's purely because the circumference of a circle is measuring how many radians we have, 2 pi radians. So kind of going through this animation one more time, we use a radius to generate a circle, and that radius generating the circle has a certain length. That certain length we then extend along the side of the circle, and that length extended along the side of the circle is what we call 1 radian. What's important about this is we have a length and we have an angle that are both the same. That length and the angle are both the same. Our angle, when we call it radians, represents the length along the circle as well. So while degrees only measure how open something is, 180 degrees, that measures how open something is, the radian actually gives us the length of that arc at the same time. And that's going to be a very, very important detail that again, degrees, while degrees are great, degrees only measure how open something is. Well, radian measures both how open it is when you understand the relationship, and it measures the length along the side of the circle. So officially, a radian is an angle whose rays subtend an arc. So subtend an arc, which has the same length as the radius of the circle. So this is 1 radian. This is also 1 radian. This is also 1 radian, but the difference is that radian, or the radius is 3. So we now have, once we know the radius, we now have the length of that arc as well. So that length is 3. And if you see what I have in blue here, that's the link to the GIF or the GIF, whichever you prefer. It's the link to that animation that I showed you. So how do we convert between degrees and radians? Excuse me. Convert between degrees and radians. If we go from degrees to radians, we want to look at what I consider like the conversion factor. This is where dimensional analysis is something that I like to refer to a lot. As I showed you before, halfway around the circle is pi radians. So if we know halfway around the circle is pi radians is equivalent to 180 degrees. So that's going to be our conversion. So if we're going to go from degrees to radians, we are going to eliminate the degrees. So let me kind of write it this way. So degrees, we multiply by pi radians over 180 degrees. And that way the degrees cancel out. As I said, this is like dimensional analysis. If we're going from radians to degrees, we just do the reciprocal. So then our radians are going to cancel out. And we multiply by 180 degrees over so many radians. So we're going to start by converting to radians. So, and again, doing all of these without a calculator as much as possible because we need to practice those fractional relationships. So we have 90 degrees. We're going to take 90 degrees, we multiply that by pi over 180, and then 90 over 180 reduces to 1/2, and we get pi over 2. That's going to be a very, very important one that we're going to need to know. So that quadrantal angle of 90 degrees is pi over 2 radians. So 225 degrees, once again, multiply by pi over 180. 225 over 180, 45 goes into both of those. So 45 goes into 225 5 times. 45 goes into 180 4 times, which is why we have that relationship of 5 pi over 4. And some of you right now are probably thinking, my mind really does not work that way. And I'm going to say, yet. It doesn't work that way yet, because as we build our angle relationships this semester, specifically next time, we're going to get into a lot more. You're going to start to have this kind of relationship too. So it's not anything special that I have. It's something that I've developed, and I'm going to encourage you to develop. So negative 30 degrees, remember that negative is just a direction, so we can really, if we want to, ignore it until the very, very end. So 30 times pi over 180, 30 and 180 reduces to 1/6, so negative pi over 6. 400 degrees, same thing, multiply by pi over 180 and reduce. This one's not quite as easy to reduce because this isn't one of those common angles that I've been referring to. So you just reduce as you need to. And again, trying to do this without a calculator is very, very helpful. So I just reduced by, cut off the zeros, so divide both those by 10. Now I have two even numbers, so negative 20 pi over 9. So the downside to radians is when you're not as familiar, you don't really understand the relationship of where that is, which is where the degrees definitely come into play. So we know the negative 400 degrees, we know negative 360, and then negative 400 would be right about there. So negative 25 over 9 would be right there. So one of the big things is, hey, should we compare it to 2 pi? So if we can compare it to 2 pi or compare it to 360, then we can kind of get that relationship. So 2 pi would be negative 18 pi over 9. So this is just a little bit further than negative 2 pi to negative 2 pi plus a little bit more, plus negative 2/9. Last one, 525 degrees times pi over 180. And it doesn't look like there's a whole lot of reducing, but 5 goes into both. So we could reduce to that. Now, if you see on this very first problem, one of the things, it's kind of a game that I like to do in my mind, where I say, okay, how do I compare this to 180 degrees? So 90 degrees is half of 180, so that would be half of pi, or pi over 2. Another way, like this negative 30 degrees. 30 degrees is 1/6 of 180, so that's why it's 1/6 of pi, and then the negative tells us it's in the negative direction. So in some ways mental games, but at the same time, it's a different way of thinking. And if you've learned nothing else from me, that having different ways of thinking about something sometimes can open it up to a lot deeper understanding. That's my hope for you. Going back to degrees, pi over 3. Officially, we multiply by 180 over pi. So pi over 3 times 180 over pi. If you want to do it in a clunky manner, 180 pi over 3 pi. Pi is reduced. 180 divided by 3 is 60. So 3 pi over 2 times 180 over pi. So again, doing it kind of like in a long manner, 3 times 180 is 540 pi over 2 pi. And then pi is reduced. 540 over 2 is 270. If you see, I've taken this to a little bit more. I said clunky. Hopefully, it wasn't insulting. It was more of, that's the official, straightforward. Hey, if you have nothing better to do, such as this problem number E, or problem letter E, 7 times 180 over pi gives us this fraction. Okay, that is a degree. 180 or 1260 divided by pi. Sure, that's a degree. that really doesn't have as kind of a, or as much of a frame of mind as what I would like to think, but that's how we do it. So it's important when we have problems, and especially when we have problems that we don't know what we don't know that relationship. Um, so anyway, the way that I think about this is I say, okay, this is like, what fraction of pi do we have? So this tool. So what fraction of pi do we have? So 3/2 of pi, or how about 1/3 of pi? So what's a third of 180 degrees? So pi over 3 is a third of pi, which is a third of 180, which is why it's 60. 3/2 pi. So what's 3/2 times 180? So we know that half of 180 is 90, so 90, 80, 270. That is an additional way of thinking about it. Anyway, get to the others. 11/6 times 180, 180 divided by 6 is 30, so 330. Negative 3 pi times 180 over pi. Pi is reduced, so that would be just negative 540. So two different ways of thinking about it. And there are not just two, there are always multiple ways of thinking about it. Anyway, I have this table of common angles. So the common angles, you should know they're common angles because they are 30, 60, 90 degrees, which come from 30, 60, 90 triangles, and then 45, 45, 90 triangles. So that 45-degree angle is going to be very, very important. And then all these other angles, 120, 135, 150, 180, they either come from the 30, 60, 90, or they come from the 45, 45, 90. So the 45 plus 90 is 135, plus 90 is 225, plus 90 is 315. So those are our 45-degree angles. Our 30-degree angles are going to be our pi over 6s. So 30 and 150, those have a relationship. So they're the pi over 6s, 210. So that's 180 plus 30. 150 is 180 minus 30. And then 360 minus 30 is 11 pi over 6. And then our 60 degrees, pi over 3. And then if we add another 60, 2 pi over 3. So that's 60 degrees, 180 minus 60, 180 plus 60, and then 360 minus 60. Those give me my pi over 3 degrees. So that's just one of our ways of looking at it. If you really, I encourage you to work with this version of those angles because eventually, and it's not going to be long before it happens, we're going to ask you to have that conversion down very, very well. All right. Our last section talks about arc length and area of a sector. So we do have some formulas. The arc length of a circle is going to be theta times r. Now, what is theta? Theta is a Greek letter that represents an unknown angle. It's kind of like the x that we use in algebra, except for when it comes to angles, we do things with Greek letters because the Greeks were really very, very proficient with angles. So it comes historically back to them. So to find the arc length, we take our theta times r. And this shouldn't be too surprising, especially because I mentioned earlier the circumference of the circle is 2 pi r. That's because they have 2 pi radians around the circle times r. Now, the important thing when you're finding the arc length is that theta has to be in radians because, remember, radians measure both openness and length at the same time, where degrees are just openness. So we need to have that length component when we're finding our arc length. So find the length of arcs intended in problem number 6. If our radius is 5 and our angle measure is 120 degrees, well, let's first convert 120 degrees into radians. That's 2 pi over 3 radians. So our arc length, which we call S, is our theta times r. So 10 pi over 3 yards. That's my little daughter in the background. So, all right. And then the SAT, what the SAT will do, the SAT will kind of present some of this information in a slightly different way, which is kind of a different way of thinking about it. So if I know the radius of my circle is 20 meters, and I know my angle is 60% of the circle, how do we find the arc length of this circle? Well, what we could do is we could say, well, what is 0.6 of 360 degrees? By the way, that's kind of a long way. So 60% of 360 degrees is 216 degrees. Convert that to radians, and we will get 6 pi over 5 radians. Now, kind of the faster approach is, well, why are we going back to degrees if we don't need to? We know that there are 2 pi radians on a circle, so 0.6 times 2 pi gives me 6 pi over 5, or 1.2, which is 6 pi over 5. So our arc length is going to be our theta, 6 pi over 5, times the radius, which is 20. Then I have a problem here where I have a dog, and by the way, this is based off of a real life situation. So I have a dog tethered to a stake by a leash 20 feet long. So let's kind of picture this. So I have, outside the dog's on a stake. So when the dog's ready to be let in the house, runs back and forth over the same patch of grass. And of course, yes, this dog did wear a big path in the grass of dirt. So anyway, the dog runs over this 1.5 radian angle. So how many linear feet of grass will I have to reseed? So I told you my angle is 1.5 radians, and then times a radius of 20 feet. So that is 30 feet of linear grass that I had to do. Problem number 8, minute hand on a clock wall has a length of 6 inches, and that is actually true. I measured it. How far does the tip of the minute hand move from 1113 to 1140? So if we kind of like get an estimate, 1113 is here, 1140 is here. So it'd be kind of useful to know what that angle is. Keep in mind, we don't actually need to know that angle, where we say, okay, we know that the full circumference that path will go around is 2 pi times 6, or 12 pi. So what we have to do is we just have to know that fractional relationship of the 2 pi r. That fractional relationship of the 2 pi r is actually a more efficient way of looking at it as how that formula comes to be. And so the reason why I have this kind of problem is because, once again, the SAT actually likes to present problems in that manner. So they test it this way. They test it a little bit more than just a straightforward, hey, do you know the formula? So it's more of like an application problem. Second thing we want to discuss is, what is the area of a circle? The area of a circle is pi r squared. We know that. Now, what's the area of a sector, though? The area of a sector is actually 1/2 theta r squared. The 1/2 theta r squared, if theta is 2 pi, we can see that the area of a circle actually models that situation. So 1/2 theta r squared. So 1/2 theta r squared. Remember, theta has to be in radians also. So find the area of a sector. Find the area of sector circle, central angle is 243 degrees. So if we take our 243 degrees, multiply by pi over 180, we are going to get our radian measure. And with our radian measure, we have 1/2 theta r squared. That'll be the area of the sector. And this one I did with the calculator, just because that ends up being one of our non-common. And honestly, there's not too many things that actually go into that as well. And then we have the clock on the wall that has a radius of 6.5 inches. So the minute hand is 6 inches, but the actual radius of the clock is 6.5 inches. So 125, the hour hand points to minute 7. What's the area of the sector of the clock between the hour and the minute hand at 125? So at 125, we have the hour hand pointing to minute 7, and then we have the minute hand pointing to minute 25. So how many minutes are in between? That'd be 18 minutes on the clock. And so 18 minutes on the clock. So what's the area of that sector? And actually on my notes here, I don't have that. So we know the fractional relationship. We have 18 minutes out of 60 minutes. We multiply that by pi r squared. So 18 over 60 times pi times 6.5 squared. So 18 over 60 times pi times 6.5 squared. And I don't have a calculator on me at the moment, or else I would do that. So there would be the area of the sector between our two hands on the clock. So that would be all for our notes today. Looking forward to seeing you guys in class next time.